Hello and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be doing a convolution example where in this example we're tasked with finding my output y of t, where the output is equated to the input x of t convolved, or the convolution operator, with my impulse response h of t. And the problem says here that x of t is denoted as cosine 3t. Now, a couple of things I want to mention. In order to understand what's going on in this example, I encourage the viewers to check out two videos that I've made in the past. The first one being eigenfunctions and eigenvalues clearly explained, and the second one being eigenfunction of continuous time LTI systems clearly explained. And what I'll do is I'll post both these videos in the top right hand side corner of this video. Similar to my past examples, what I encourage the viewer to also do is pause the video and see if they can solve this example, then come back to the video and see if they receive the correct answer. So to begin, the first thing we want to do is find the impulse response h of t located here. And we know that the impulse response of a system, capital H, is the output of that system when my input x of t is the Dirac delta function. So just as a refresher, we say that y of t is equated to h of t, which is this impulse response, when my system, capital H, has an input x of t, where x of t is this delta function, delta t. So essentially we denote this as h, where my input is delta t. From the previous slide, we said that the system h is denoted, or is basically the integral from negative infinity to t of my input x tau d tau. So again, that means that the impulse response h of t is equated to this integral from negative infinity to t when x of tau is delta tau d tau. And I'm going to go ahead and prove this. But essentially, this is the fundamental property of the Dirac delta function that says that the integral from negative infinity to t of the Dirac delta function is equated to this unit step function ut. So you might ask yourself, why is the impulse response of this system basically the unit step function? So let's go ahead and prove this. And we say that imagine you have a function delta t. And essentially, this delta t is an impulse that shoots up to infinity at exactly 0. And my timeline here is t. I'm going to go ahead and prove that the integral of this function is equated to my unit step function simply by observation. So the first case we take is when t is less than 0. We say that the impulse has not occurred yet. So the accumulated area is equated to 0. So if you consider a time where we're taking the area of this for t is less than 0, the function hasn't occurred yet. So we simply get 0 as my solution. Now the second case is when we consider for t is equated to 0. We say that the impulse, because it's this special function, the impulse has contributed a total of an area equated to 1. So my area is equated to 1. So essentially at this exact point 0, this function delta t has equated an area equated to 1. And lastly, the third case is when t is greater than 0. We say that the integral / total area has accumulated a value of 1 and holds that value. So for t is greater than 0, it's essentially this entire area, including my function and what's remaining here. So my area is equated to 1. So in conclusion, or therefore, we say that the output jumps from 0 to 1 and stays there, similar to a unit step function, right? So u of t is equated to 0 at t less than 0 and 1 for t greater or equals to 0. And again, just to be clear, this here, h of t, is the impulse response of this system, capital H, because my x of t is this delta t. So the impulse response h of t is equated to u of t. or the unit step function. I hope this makes sense. This concept is very important to understand in engineering. So if you have any concerns or questions, please leave them down in the comment section below and I'll be sure to get back to you. Okay, given that we know our impulse response, h of t, we can then say that y of t is equated to x of t convolved with h of t, which is simply cosine 3t convolved with u of t. And from a previous video we studied, we know that the convolution of two functions is the integral from negative infinity to infinity. In this case, it's going to be x tau times h t minus tau d tau. So if we substitute for x tau and h t minus tau, we're going to get that y of t is equated to the integral from negative infinity to infinity cosine 3 tau u t minus tau d tau. So now we need to ask ourselves, what does this function u t minus tau look like? And we need to realize that t here is some constant and our variable or our independent variable is tau located here. So I can say that u of tau we know is 0 for tau less than 0 and 1 for tau greater or equals to 0. So then u t minus tau is equated to 0 for t minus tau is less than 0 and 1 for t minus tau is greater or equals to 0. If we go ahead and solve for tau in this case here, we get that tau is greater than t. And for this case here, we get that tau is less than or equals to t. And again, remember, t in this case here is just a constant. So if we're to plot this function here, I can say that it'll look something like this. So we get u t minus tau, where my x-axis is tau. And let's say this point here is a point t. So it's 0 for tau greater than t. So it's 0 all the way through here. And then it's 1 for tau less than or equals to t. So it shoots up and we get a 1 for tau less than or equals to t. And again, this makes sense because if tau is equals to t, we get u t minus t, which is equated to u of 0, which is simply 1. So when tau is equals to t, it shoots up to 1. So then this here is equated to the integral of negative infinity to t cosine of 3 tau d tau, where again, we're taking the integral between negative infinity, which is this direction, and stopping at t, because anything other than that is simply 0, so we don't care about, so that we can get rid of this function here. And to continue, the integral here of cosine 3 tau is going to be sine of 3 tau over 3, where our conditions are from negative infinity to t. So then this is equated to sine of 3t over 3 minus sine of negative infinity over 3. And what we say is that this quantity here does not exist since the sine function oscillates between -1 and 1. In other words, for some value of our independent variable here, t, this function here is not a single value. So then to conclude this, we're going to say that let's take a practical causal input where my t starts from 0 and not t is equals to negative infinity. So essentially consider that this t here maybe is around 5, and we cut this to be starting from t is equals to 0 and not t is equals to negative infinity, which is a more practical scenario. So in that case, I can say that y of t is equated to sine of 3t over 3 minus sine of 0 over 3, or simply 1 over 3 sine of 3t. So in this example here, where we take a practical causal input, this here is my solution. Okay, so the last thing I want to do is prove that convolution is commutative. And essentially this means that if I take y of t is equated to x of t convolved with my impulse response h of t, I get the same answer if I take h of t convolved with my input x of t. So then we can say that y of t is equated to my impulse response h of t is this unit step function ut convolved with my input, which is cosine 3t. If I go ahead and use convolution, I can equate this to the integral from negative infinity to infinity of u tau times cosine 3t minus tau d tau. So then now this is equated to the integral from 0 to infinity. This allows this function to go away. So then we're left with cosine 3t minus 3 tau if I distribute the 3 d tau. This integral is equated to, the integral of cosine is sine. And I repeat what's inside my parentheses. So this becomes 3t minus 3 tau. And then I divide it by the derivative of the thing inside my parentheses. So since this here is just a constant, it becomes 0. And then the derivative of minus 3 tau is simply minus 3. And my limits are from 0 to infinity. So if I go ahead and plug this in, I get that this is equated to sine 3t minus infinity over minus 3 minus, and this becomes sine 3t minus 0 over minus 3. This here is a plus plus. So then this is equated to sine of minus infinity over minus 3 plus sine of 3t over 3. Similar to the previous slide, if I take a practical causal input, where in this case, t actually has a limit equated to t, where essentially here, having my integrals operand go all the way to infinity, I restrict it to t. All right, let's go ahead and see what we get. So now y of t is equated to sine of 3t minus 3 tau over minus 3 from 0 to t. So then this becomes sine of 3t minus 3t over minus 3. And again, minus sine of 3t minus 0 over minus 3. This is plus plus. So then this is equated to, this is sine of 0 here. So then this function goes away to 0. And then we get the same answer as we did before, which is 1 over 3 sine of 3t. And this ends our proof that convolution is commutative. Okay, in the next video, what I'm going to do is, instead of using convolution, I'm going to use multiplication using eigenvalues and eigenvectors, which we've studied in the past. If you have any questions or concerns about this video, please leave them down in the comment section below, and I'll be sure to get back to you. If you like the video, please give it a thumbs up, and please share the video to your colleagues and friends so they can also obtain the knowledge provided in the video. And lastly, if you like the content the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.